Hey everyone, welcome back to the channel. If you've ever had a three-phase motor trip out, hum and not start, or just quietly die on you mid-shift, this video is for you. Today I'm walking you through a complete troubleshooting process for three-phase motors. We'll cover the tools you need, the safety steps you can't skip, and a step-by-step method to go from something's wrong to here's exactly what failed, whether that's the motor itself, the wiring, or the control gear feeding it. If you're in maintenance, electrical work, or just like understanding how this stuff works, hit subscribe. Let's get into it. Before you touch anything, this section is non-negotiable. Lockout, tag out the motor and its disconnect. Verify zero energy with a meter. Don't just trust the switch position. Assume capacitors can hold a lethal charge even after power is off. Wait the manufacturer's discharge time and verify with a meter rated for the voltage. Wear appropriate PPE insulated gloves, safety glasses, and arc flash rated clothing if you're working on or near live panels. If the motor is hot, seized, or smells like burnt insulation, treat it as a bigger fault. Don't just reset and re-energize blindly. That's how motors and sometimes people get hurt. Got your PPE and your meter? Good. Let's start the actual diagnosis. Before you open anything up, talk to the equipment, figure out what it's telling you. Ask yourself these questions. Did it fail suddenly or was there a warning? Noise, vibration, smell, overheating trend. Does it hum but not turn? That usually points to single phasing or a mechanical bind. Does it trip the overload or breaker immediately? That's often a short or severe overload. Does it run but underperform a circumflex euros? Slow, weak torque overheats under load. Any burning smell or visible smoke or scorch marks? That's insulation breakdown. Stop and inspect before re-energizing anything. Write these symptoms down. They'll save you time because they point you toward electrical, mechanical, or control circuit problems before you even pick up a meter. With power still locked out, do a physical inspection. Check the nameplate data, confirm voltage, full load amps, and frequency match your supply. Sounds obvious, but wrong motor or wrong wiring configuration causes real failures. Check the enclosure and terminal box for moisture, corrosion, burnt terminals, loose connections, or chewed wiring. Rodents are more common than people think. Try to rotate the shaft by hand. Feel for grinding, tight spots, or excessive play. A seized or notchy bearing is a mechanical fault, not electrical. Check the cooling fan and vents. Blocked airflow causes overheating that mimics electrical faults. Check the coupling, belt, or load side for alignment and anything jamming the driven equipment. A high percentage of motor failures are actually the load binding up. If everything looks physically fine, it's time to bring in the meter. This is the core of the video, so let's go through it methodically. Still locked out for the first two tests. Test 1, insulation resistance using a Megger test. Disconnect the motor leads from the supply. Use a megometer at the correct test voltage for your motor's rating, usually 500 volts DC for standard low-voltage motors. Test each phase winding to ground or to the frame. As a rule of thumb, readings should generally be above 1 megohm per rated kilovolt, though always check manufacturer specs. Very low readings mean moisture or breakdown in the winding insulation. The motor likely needs drying out or rewinding. Test 2, winding resistance, using continuity or ohms. With the meter on ohms, measure resistance between each pair of terminals U to V, V to W, and W to U. All three readings should be nearly identical. Small imbalance is normal, but more than about 5% difference between phases suggests a winding fault, such as shorted turns or a bad connection. Infinite resistance or an open circuit on one phase means an open winding, often the cause of that hums but won't start symptom. Test 3, checking for grounded windings. Measure resistance from each terminal to the motor frame or ground. It should read essentially infinite or open. Any continuity to ground means the winding insulation has failed and is shorting to the frame. Test 4, live voltage and current checks. Power is now restored, so use extreme caution from here on. Check the voltage between all three phases at the motor terminals. It should be balanced within about 1 to 2%. Significant imbalance stresses the motor and can indicate a supply-side problem, like a loose connection or a blown fuse upstream. Check the current draw on each phase with a clamp meter while running under load, and compare it to the nameplate full load amps. Also compare phase-to-phase current balance-imbalance above roughly 10% points to a developing fault. If one phase shows zero voltage or zero current while the others are normal, your single phasing check upstream fuses, contactor contacts, and terminal connections. Test 5, the control circuit check. Don't forget the motor starter itself. Inspect the contactor contacts for pitting or burning. Check the overload relay settings against the motor's actual full load. A misconfigured overload will nuisance strip, or worse, fail to protect the motor. If it's VFD-driven, check the drive's fault log first. Most drives will tell you exactly what tripped, whether that's overcurrent, overvoltage, or a ground fault. Let's tie the symptoms to causes so you've got a mental checklist. If it hums, doesn't turn, and shows high current on one phase, that's likely single phasing, an open winding, or a blown fuse. If it trips the overload immediately, that's likely a locked rotor, a mechanical bind, or a severe overload. If it runs but overheats, that's likely a voltage or current imbalance, blocked cooling, or an overload. If you get low insulation resistance, that's likely moisture or insulation breakdown. If there's vibration, noise, or a mechanical feel, that's likely bearing wear or misalignment. And if you're getting random nuisance tripping, that's likely a loose connection or marginal insulation. The pattern to remember. Symptoms first, then visual and mechanical inspection, then electrical tests from simple to complex. Don't jump straight to replacing the motor. A huge number of dead motor calls turn out to be a blown fuse, a loose lug, or a jammed pulley. That's the full troubleshooting process: safety, symptoms, visual inspection, then a structured electrical test sequence. Follow that order and you'll catch the fault fast instead of guessing and swapping parts. If this helped you out, drop a like, subscribe for more hands-on electrical and maintenance content, and let me know in the comments what motor issue you're dealing with. I might cover it in a future video. Thanks for watching, and I'll see you in the next one.